Hello everyone. Today we are going to see symmetric key distribution using key distribution center. First let's understand what is symmetric key distribution. Symmetric key distribution is the process of securely sharing a secret key between two parties so that they can communicate using symmetric encryption. In symmetric encryption, both sender and receiver use the same key for encryption and decryption, but the main challenge is how do we share the key securely over an insecure network. If we send the key directly, an attacker can interrupt it. This can lead to attack like man-in-middle attack, where the attacker secretly listens to or alter the communication. To solve this problem, we use a trusted third party called Key Distribution Center or KDC. A key distribution center is a trusted central authority that helps to user share a secret key securely. Instead of user exchange key directly, each user shares a secret key with the KDC. When two users want to communicate, the KDC generates a temporary key called session key and securely sends it to both users. In this way, the key is never exposed directly over the internet, making communication more secure. Now let's understand what are the problems and its solutions. Let's see problem first. Two users, Alice and Bob, want to communicate securely over a network, but the network is insecure, which means attacker can listen or interrupt the communication. So the main challenge is how can they share secret key safely? If Alice sends the key directly to Bob, an attacker can capture it. This makes the system vulnerable to attacks like eavesdropping and man-in-middle attacks. So direct key exchange is not secure. Now the solution is we use a trusted third party called Key Distribution Center or KDC. Instead of sending the key directly, both Alice and Bob communicate with the KDC. The KDC securely generates and distributes session key to both users. To make this process structured and secure, we use Needham-Schroeder protocol, which defines the steps for safe key distribution. So the help of KDC and this protocol, secure communication can be established even over an insecure network.
The slide explains how Alice and Bob securely communicate using a trusted server called KDC. In first Diffie-Hellman, both sides agree on some public values and choose their own secret numbers. They exchange computed values and generate the same shared secret key without even sending the key itself. In the next slide, we can see that Needham-Schroeder protocol uses the same idea to create a secure session. The Alice asks the KDC to connect with Bob. The KDC generates a session key and sends it securely. The Alice forwards part of it to Bob. The Bob sends a challenge to verify Alice. The Alice responds to the challenge correctly. The Bob verifies and the connection becomes secure. In the overall, Diffie-Hellman helps to create a secret key and the Needham-Schroeder ensures both users are authenticated and communication is secure.
Okay, so starting with the server, this is basically our KDC. It creates a socket, binds it to the localhost on port 5000 and just waits for clients to connect. So this is like the central trusted authority in our system. So next, when client connects, the KDC performs Diffie-Hellman. It generates a random secret, computes a public value, exchanges it with the client, and both sides end up with the same shared key. The important part is this key is never actually sent over the network. Now this is where the main protocol happens. The KDC receives Alice's request, extracts her ID, Bob's ID and the nonce. Then it looks up their master keys and generates a fresh session key and timestamp. So next, client. On Alice's side, the same Diffie-Hellman process happens. She generates her secret, exchanges values with the KDC and ends up with the same shared key. When Alice types connect, this message is created with her ID, Bob's ID and a nonce. This is basically step 1 of the protocol. She receives the response from the KDC and decrypts it using her master key. From that, she extracts the session key and the inner message meant for Bob. This part checks the timestamp. If the message is too old, it gets rejected, which prevents replay attacks. Now Ally sends Bob his encrypted message, receives a nonce, challenge, modifies it, encrypts it, and sends it back. This proves she actually has the session key. Once verified, they enter a secure chat loop where every message is encrypted using the session key. Next, Bob. Bob starts in waiting mode. When Ally connects, he decrypts the message using his master key and extracts the session key. He also validates the timestamp. If it's expired, he rejects the connection immediately. Then he sends a nonce challenge. If Ally responds correctly, he knows she is legitimate and sends verified. Next. This is our simplified DES algorithm. The S boxes are used for substitution, which adds security. This part generates subkeys K1 and K2 from the main key. This follows the Fischl structure: split, process, swap, and combine. Decryption is the same process but with keys in reverse order. This wrapper converts the text into binary, encrypts it block by block. And this converts it back into readable text after decryption. Now let's look at the replay attack. This is where an attacker reuses the old messages. Here the attacker captures a previous encrypted message and replaces it to Bob. Since there is no timestamp, Bob accepts it as a valid. If the attacker also knows the session key, they can successfully impersonate allies. To fix this, we add timestamps. Now Bob checks if the message is recent. If it's too old, it gets rejected, so the replay attack fails. Now I will run the complete demo script which shows the three phases: normal execution, replay attack, and prevention using timestamps. This is the normal execution of the Needham-Schroeder protocol. Here we can see the test data, Ally's key, Bob's key, IDs, and generated nonces. Ally sends a request to the KDC, and the KDC generates a session key and prepares encrypted messages. Ally decrypts the response and forwards Bob's encrypted message. Bob then decrypts it and retrieves the same session key. Bob sends a challenge nonce. Ally responds correctly, and Bob verifies it. You can see the verification passed message here. So authentication is successful and a secure communication channel is published. Now we simulate a replay attack. Here an attacker captures an earlier encrypted message sent from Alice to Bob. The attacker replays the exact message later to Bob. Since there is no timestamp, Bob has no way to know this message is old, so accepts it and believes it is from Alice. If the attacker has also compromised the session key, they can respond correctly to Bob's challenge. The replay attack was successful. So to fix this issue, we include a timestamp inside the encrypted message. Here Bob receives a fresh message and checks the timestamp. Since it is within the valid time window, he accepts it. Now the attacker tries to replay an old message again, but this time Bob compares the timestamp with the current time. The timestamp is outside the allowed window, so it considered invalid. So Bob rejects the message and the replay attack is prevented. This ensures message freshness and protects against the reuse of old messages. So from this demo, we clearly see that without timestamps, the system is vulnerable, but with timestamps, replay attacks are effectively prevented.
Finally, to conclude our project, we successfully implemented a secure key distribution system using the Needham-Schroeder protocol with the key distribution center. The main objective was to enable two users to communicate securely over an insecure network without directly sharing the keys. To achieve this, we used a trusted third party, the KDC, which generates and distributes session keys safely. We also incorporated the Diffie-Hellman Key Exchange to establish master keys securely without transmitting them, adding an extra layer of protection. Through this process, we demonstrated how encrypted messages and nonces ensure authentication and prevent unauthorized access. We also highlighted the concept of replay attacks and showed how timestamps can be used to overcome such threats. Overall, this project helped us understand how secure communication is established, how cryptographic techniques work together, and how real world systems maintain security. In conclusion, this project serves as a simple yet powerful demonstration of how cryptography is applied in real world applications like secure messaging, banking, and network systems. Thank you for listening, and we hope this presentation gave you a clear understanding of secure key distribution using KDC.